Okay, so today we're talking about the chemical senses. Okay, so taste and smell. So we've already talked about the eyes, the vision. Now we're doing taste and smell. Next week we'll do everything in the ear, which is hearing, but also balance, proprioception, all of that. Okay, so we'll start with taste. So taste buds. Infants have around 10,000 taste buds, and adults, by the time you get to adulthood, you're down to about 3,000. Okay, so in a way, our little guys are really like super tasters, right? And there's a couple pictures of my kids. Um, they literally feel the world through their mouths, right? They put everything in their mouths, they lick everything, they're biting on everything, right? Soren, this is Soren, who's now almost 16 and as tall as me. But when he was a baby, we just stopped taking him to the beach after a while because he would literally just eat handful after handful of sand. He would just never stop eating sand the whole time we're at the beach. And then it comes out in their diapers and you got to wipe it. It makes it, it's pretty uncomfortable. But he would just taste everything. And then this one is Christian. But this is what happens. I don't know. Have any of you babysat for like little ones like this? Yeah, and a lot of times when you're introducing a new food to them, a new solid food, this is the face they give you when they first taste it. It's like, it's like the worst thing ever, but then they want more of it right away too. Right? And so it's like, there's just tastes are very strong to babies because they have so many taste buds. They're really like super tasters for sure. And so, yeah, couple of my little ones there. No Eve picture in there, just the boys. But yeah, anyways. So our taste buds are composed of 3 types of specialized cells. And so it's part of our epithelial tissue. If we go back to our histology section last time, okay? Um, and so we have what are called our taste cells or our gustatory cells. Okay, so these are the actual receptors that are kind of on the end of the neurons. Okay, and they have little microvilli on them, like little hairs. That's what actually increases the surface area and then allows for the interaction of the chemicals with them. Okay, so these are turned over very rapidly. They only last about 10 days and then we make new ones constantly, okay? And then we have the supporting cells that are kind of around those. These give shape to the taste bud and kind of hold them in place. And then we have the basal cells underneath them, which are important because of that high turnover rate that we need to constantly replace those cells that get damaged by mechanical forces in your mouth or chemical stress in your mouth of certain things you're eating, hot foods, certain strongly low pH foods, those things can damage these and they need to be replaced a lot. So we got to have stem cells right there ready to replace all of these. Okay, so that's kind of everything that's in the taste buds. Okay, we good there? We wrote that down. Okay, and then taste buds are found in papillae. Papillae are these little bumps on the surface of the tongue. Okay, those of you that have cats at home know that cats' tongues are super rough, right? How many people have had your cat lick your finger and you're just like, oh my gosh, it's so rough. It's like sandpaper, right? Cats' papillae are sharper and more rigid than ours, but it's the same idea. We have these bumps on their tongues, and so give our tongues this rough texture. And most of the time contain taste buds. They don't all contain taste buds though. So there's 4 primary types of papillae on our tongues. So the filiform ones are the smallest ones. This is really what provides the friction part of our tongue and kind of allows us to grip things with our tongue. Those are the ones that don't have any taste buds there. But they do have touch receptors. So we can feel things in them, but we don't actually taste things because of those. And then we have the other 3 types that do have taste buds inside of them. So there's this big V-shaped pattern, these big ones kind of in the back, the circumvallate, and then the fungiform ones only have about 5 taste buds each, and then the foliate papillae that have a bunch of taste buds as well. Okay, so this next slide just has you label those things. So go ahead and yeah, and send in go ahead and label those, fill those in, and send in that answer on your clicker. Which type of papillae would contain the most taste buds out of the ones you've got there? And if you noticed on your canvas that you had a 0 on the IRAT, that's because your clicker's not registered right. Okay, so there are two people in class that still don't have their clicker registered right. So just come up to me after class and talk to me. If you haven't looked yet on Canvas, just check that. But there's just two of you, but that means that your clicker's not associated with your name, and that's why you have that 0 there. Okay, so go ahead, talk through this and send this in when you're done.
So it could be.
Yeah, you're one of them. Yeah, yeah, you are. It'll all sync up once you register, so it's all saved. It's just right now I don't know who you are based on your clicker. So yeah. Yeah. So there's two parts. There's the part of making the online account, and then you connect to our course. Did you find BIO 1040 Sawyer? Okay, and then the second part is you go into your profile and add your clicker number to your profile. That might be the part you haven't done yet.
Yeah.
Yeah, for sure. Thank you. Mhm. All right, go ahead and send that in on your clicker, please. All right, I got 40 people. Anybody else? Go ahead and send it in if you haven't yet. 42. All right, I'll leave it open for a sec. I got 43 out of 48. That's pretty close. So about half of you are saying D, and then we have about 10 to 15% saying A, B, and C each. So let's talk through these first. So we've got A being those circumvallate papilla. Okay. B are the fungiform papilla. Okay. C are the filiform papilla, and then D was the foliate papilla. And so most of you said D. So if we go back up to the previous slide, we see these foliate ones have over 100 taste buds. So those are definitely the ones that have the most, right? So D was the correct answer there. Okay. And one thing that I would love to ask you all to do in this class is put your phones in your backpacks. Okay. It's so common for us to just, when we sit down for a class or a meeting, to stick our phone on our desk. But it distracts us whether we like it or not, just because it's sitting there, right? We're thinking about it, and we're wondering if something's going to happen with it, right? It's just right there. And there's studies that show this, that when somebody's phone is on their desk, they're distracted, whether somebody's calling you or texting you or not, you're distracted by it. And so you're here to learn. So let's just put our best foot forward and do everything we can to not be distracted during these 50 minutes. Yeah, go ahead. Yeah, A. So let's go to A. So the circumvallate ones. Yeah, so each have 100. Yeah, they're kind of the same, right? Yeah, so this one is saying over 100 taste buds, over 100 taste buds. Yeah, so it could be either one, really. Yeah, yeah, good point. It could definitely be either. There's no differentiation between that and that. So thank you for pointing that out. Yeah, yeah. Okay, let's go D or A then. Thank you. Okay, other questions or comments on this? Okay. All right. So then the taste buds themselves, they're shaped like a gourd. This is a gourd right here. So kind of bigger on the bottom, smaller on the top. Okay. They have a little pore, a little hole on top that lets the chemicals in. Okay. And then these little gustatory hairs are in the pore. Okay. lots of saliva. The saliva is important because it breaks down the chemicals we're eating and frees up the chemicals so then they can bind to the receptors, okay? So most of these are on the tongue, as we've just been talking about, but we also have taste buds on the roof of our mouth, in the soft palate, okay? We have them on our inner cheeks, in our throat, in our pharynx, and then even some on our epiglottis, the thing that covers up our larynx, covers up our respiratory tract. So we kind of have them all over, not just on our tongue. The next slide is another opportunity to label those things specifically in the taste buds. So once you're done writing this stuff down, you can go to that next slide and start filling that in. And I'll open up the clicker for you to send in all three, is it three? All three letters there, just in the right order. Somebody next to you can help you do that if you're not sure. You put in those three answers in your clicker, then hitting send. You can put in one answer, then you use go to the right, put in the next one, go to the right again, put in the next one, then hit send. All right, go ahead and send that in if you haven't yet. All right, everybody hit send. I've got 29 out of at least 44 of you that responded to the last one. So just hit that send button whenever you're ready there. And I did do a quick look of Ashley's question about do your pupils dilate when you see something that's someone that you like or something that you like. And it does look like there's some science behind that with a release of oxytocin, which is a hormone we'll talk about soon, which is related to bonding, emotional bonding, and a release of neurotransmitter dopamine we talked about last semester. Both of those can dilate your pupils a bit. So feelings of attraction and love can actually do that. So yeah, great question, Ashley. I love that. I love that. No pun intended. Okay. All right. What do we got? Let's see. Yeah. So we got about, yeah, we're kind of all over the place here, but the order is a little bit off. So yeah, what do we got? Okay. A little bit all over the place. I can't really summarize that one quite as easily. About 13% of you are putting DBA, which is the one that I would say as well. So the blank cells are there to support and protect the receptor cells. Okay, so D is support and protect. So those would be, if we go back to the ones here, right, those supporting cells, right? So we're talking about there, support, protect, give shape. Okay. Next one, the blank cells are there to sense chemicals. Okay. So B for that one. So B, the only reason we can tell that is because they're attached to a neuron, right? That's how we can tell that. Okay. Receptors there, sensory receptors attached to the neuron. Okay. And then the blank cells are there to replace damaged receptor cells. That would be the one that's kind of lowest down there. And so that's A, that's these big basal cells there. Okay, C is just the microvilli itself, the little hairs that stick out. And then E is just the pore. It's just like the hole that allows the chemicals to go in there, right? And then F, what's F? Just a neuron, right? Those sensory neurons that drive our taste sensation and send it up to the brain. Go ahead, Alyssa. B, B is the actual gustatory cells. So if we go back to match it up with this slide, it's this one right here, these gustatory cells. These are the actual taste receptors, the things that bind to the chemicals to be to then activate the neuron and then send that signal up to your brain so you are aware of the taste. Other questions on this? Okay. Everybody good here? Okay, so let's talk a little bit more about taste. So there's five main tastes that we can taste. So sweet, salty, sour, and bitter. And then somewhat recently, not super recently, but it wasn't known for a long time, umami is kind of the fifth taste. And so sweet is obviously going to be sugars, right? Salty is going to be more ions and metals, whereas bitter is going to be things that have a higher pH. So basic substances, alkaloids, okay? And we're much more sensitive to bitter than we are sour. Okay. Oh, sorry, the sour one. I forgot that one. Sour is acids, bitter is alkaloids. We're much more sensitive to bitter things, and that's because most naturally occurring chemicals that are poisonous, like plants and things like that, tend to be higher on the pH scale than lower. And so we need to be ready to not want to eat those things, right? And so same thing with most medicines, right? If you put some kind of pill in your mouth that's not coated with sugar, like the Advils are, then it tastes really bitter, right? And it's the same idea. It's definitely a lot of any of those things will be poisonous. And then umami is mostly meats, amino acids, things that are rich in protein, and that's like the savory flavor that we get with those kind of foods. So it says amino acids and then especially glutamate. And then I just had meats right there. Savory flavors that we get from those. Go ahead, Melissa. MSG, yeah, I believe MSG is a pretty salty flavor, but yeah. Say it again. Yeah, it's more of a preservative, is my understanding. But yeah, it's the thing that, most Asian foods had a lot of MSG in them, a lot of like packaged Asian foods did, but now most of them will say it doesn't have MSG anymore, right? Because it was kind of at high levels, it was shown to lead to some cancers and things like that. But my understanding was that it was a preservative more than anything. Yeah. But I think it did also add to the flavor in some ways too, but yeah, yeah. Other questions on that? Okay. All right, so yeah, other tastes that are interesting, they're kind of outside of the normal realm of taste would be like mint and spicy, okay? And the interesting thing about these is they're kind of actually tricking our brain into thinking that our mouth is getting hot, okay, or cold. So with minty flavors, these are actually chemicals that activate the cold receptors in our mouth. And then spicy foods activate the warm receptors in our mouth. Um, and they kind of just trick our body into thinking we're hot or we're cold, even though it's not an actual change in our temperature. It's just activates those receptors. So capsaicin is the thing that is also in like icy hot or things like creams that you rub on your sore muscles. And menthol is what gives you the cold part of icy hot, which is also kind of has that minty type feeling. But yeah, capsaicin activates warm receptors, and that can actually block pain in some ways too by kind of your spinal cord prioritizing the feeling of that instead of the pain. But yeah, is there a question over here? Got it? Yeah. Like what? Good question. No, it's not. It is literally like activating the same receptors that you would activate when you put hot tea in your mouth, right? Like it's the same kind of thing. So it's telling you your brain is getting the exact same signal that it would when you put something really hot in your mouth, right? But then it kind of can spread. You kind of can spread your whole body. You can kind of get sweaty and stuff too, which is interesting as well. But that is partially because capsaicin gets into your bloodstream and then it activates warm receptors all over your body too. And so you start feeling hot, even though your body temperature probably isn't actually increasing. So yeah, but there is definitely like adaptation to it for sure. Yeah, we led a LoveWorks trip to India this past summer, and Indian food is just so much spicier than anything we have here. But like little kids that are like 4 years old are just like chowing on this stuff that like we can't even touch, because they've been eating that food since they were born pretty much, and so there's definitely like an adaptation that can happen for sure. Yeah, Taylor.
Why does your nose run to when you eat spicy foods?
Yeah, that's a good question. Yeah, yeah. What that is, I think, yeah, that's a good question. I'm sure it has something to do with like autonomic nervous system activation. But yeah, I'll look that one up too. It's another good one. Yeah, yeah, for sure. Go ahead. Yeah, I think it's something to do with the fats. So capsaicin is kind of like an oily substance, and so the only way to break down an oily substance is with other fats, other lipids. And so like when you try to mix, water with something oily, it doesn't do anything; it just separates. But when you mix other fats with something that's also a fat, then that can help kind of dissolve the substance, and so that's what milk can do. Yeah, yeah. Other questions? Okay. Okay, yeah, and then this was kind of a myth that was around for a long time that we only taste sweet on the front and bitter on the back, sour on the sides. It's not true. Our taste receptors can sense all of the different flavors throughout the tongue. Yeah, Katie.
Sour and it's tasty, but it changes
Hmm. I think that's just like layers on the candy. Yeah, like no, I think it's like the outer layer is like sugar, and then you kind of melt through that, and then the inner layer has like the sour stuff on it. That's oh. Oh, okay.
But they like
Oh,
put it to it.
okay. I haven't heard of that. Yeah, yeah. Okay. Send me a link to something on that. I'd like to check that out. Yeah. Not that I want to try it. I want to understand it, but yeah. Okay. No, I haven't heard of that. Nice. Other questions or anything? Okay. All right. So then, as we've kind of already talked about with babies, we definitely have, even at the level of adults, we have people that are much more sensitive to taste than others. And so we definitely have like super tasters, people that taste things really strongly. And it might just be that they have more of those fungiform papillae and then more taste buds. There's a couple unique tastes that certain people taste one way and other people taste another way. So narangan is one of those. This is a chemical that's found in grapefruit. And so some people just can't even touch grapefruit at all because it's so incredibly bitter. And then some people don't really taste the bitterness in grapefruit, and it has to do with just a genetic difference in the receptors that receive that chemical. And then as we age, we decline in the number of taste buds that we have. Yeah, Caden?
That's similar to like cilantro tastes like dope.
Totally, yeah, yeah, and that one is, but that one's actually a smell thing. We'll get to that on the smell part. Yeah. Yeah. Okay, so the neuron pathway for taste. Um, First of all, we receive the chemicals on the receptors, right? And then that causes depolarization. So we have a couple different ways this happens. Some of the types of taste that we receive use the second messenger system. If you remember what that is. Well, I don't know why I did that. Use the second messenger system. So we activate a receptor, goes inside of that little receptor cell, and then opens up an ion channel, and then that starts an action potential. That would be the second messenger system. But then some directly activate, for example, when you eat sodium chloride, like salt, sodium is the thing that rushes into our cells to make action potentials, right? Everybody remember that last semester? Yeah, sodium influx leads to depolarization. So that's actually how salt receptors work, is sodium just rushes in, activates the neuron, and we taste salt, right? So some kind of have that direct activation, and then others have a different way to do it. And so, yeah, so all of this goes up to what's called our gustatory cortex, which is on the frontal, in the frontal lobe of our brain. And then we have three primary nerves that send the signal from our taste buds up to our brain. And so the anterior 2/3 of our tongue is cranial nerve 7, our facial nerve. The posterior part, the back 1/3 is glossopharyngeal 9. And then the other ones are like in our throat and around that area. Those are all connected to the vagus nerve, cranial nerve 10. All right, questions on any of this? Okay. All right. Yeah, so I just kind of gave this one away. Sorry, I got too excited. But we can yeah, this is what I was just talking about, right? How eating crystallized sodium chloride could directly lead to tasting a salty taste. Again, it's that sodium influx that leads to an action potential. Right? So we don't need to activate some receptor on a cell in our tongue. The sodium just goes right into a pore that depolarizes that cell, that activates the neuron, and we get a signal that goes up to the brain. Okay, so that's an example of direct stimulation, and there's other examples as well. Some of our sour flavors are that way too, with hydrogen ions. Hydrogen ions that are released by acids. Again, that hydrogen can just rush right in, depolarize the membrane. Calcium can do the same thing. But yeah, so there's just a couple other examples of that. So in taste, we either have this direct stimulation method, or also can use that second messenger system. Okay, so with smell, we'll move on now to smell. The epithelial layer here is called the olfactory epithelium, whereas in the mouth, it was called the gustatory epithelium, right? And so specialized epithelial cells up in the superior part of our nose, okay? We have somewhere between 10 and 20 million of these receptors, okay? So just way, way more than we have for taste. Okay, the interesting part about it is just normally breathing in with your nose, the air just kind of goes this way, right? And so when you really want to smell something, we all do this naturally, but we sniff like that because we try to make the air kind of spiral a little bit, and because we have to kind of churn it up to get it up to where our sensory receptors are. And those of you that have dogs know this too, right? Dogs are going around after dinner. At least that's the case with us, because we have kids that are dropping food on the floor all the time, and our dog is just going around sniffing everything, and you can just it's like a little vacuum cleaner, nose to the ground, trying to find everything, right? But yeah, because it kind of requires this hairpin turn for the air to get up in there where the receptors actually are. And then you guys may remember last semester when we looked at the bones of the head, we had in the ethmoid bone, there's a cribriform plate. You guys remember that? Sound familiar? Yeah. And then on both sides of that little perpendicular plate, that thing that's stuck up in the middle, there's a bunch of little holes, right? And those holes are what allowed these little little extensions of these neurons to go through from the olfactory bulb, and then the receptors are on the ends of those neurons. Okay, so cell types in the olfactory epithelium. Okay, so we have the receptor cells themselves. Okay, we have the supporting cells and the basal cells. So very, very similar to what we just talked about in the mouth, right? Got the ones that actually receive the chemicals and connect to the neurons. We got the ones that are just there kind of physically supporting the cells. And then the third is the ones that are there to replace the damaged receptor cells. Okay, so these also have a constant turnover, not as rapid as in the mouth, because there's not as much physical pressure and other things that go in our mouth or in our nose to destroy these. So they get turned over every 60 days. And then again, we have cilia that's in mucus. That chemical gets kind of churned up and goes up into the mucus and then gets dissolved. So then those receptors can sense those chemicals. Once you're done writing this down, oops, sorry. Once you're done writing this down, you can go to the next slide and start filling that in, just a labeling of this olfactory epithelium. And then there's one to send in there in your clickers as well. All right, so yeah, go ahead and work with your team, fill this in, label this, and send in the one on your clicker that answers that question on top there. All right, you'll need to hit the send button with this type of question just because F is an option.
I love.
Quick update on the spicy food, runny nose situation. Capsaicin doesn't only activate your warm receptors, but also irritates the mucous membrane of your nose. And so then your mucous membrane starts producing a bunch of extra mucus when it gets irritated, which helps to clear it out, right? It's trying to clear out that chemical that's irritating it. So there's your answer. Thanks for helping me learn too. I love it. Okay, what do we got? Anybody else? Go ahead and just hit send to make sure. I got 41 of you. Good. So about half of you are saying B, and then a few saying D. But let's take a look here. So A is what we saw. We saw that in the sheep brain last semester, the olfactory bulb, right? Remember those olfactory bulbs that came up? Which cranial nerve is this? Which one? Uno, yeah, one. There you go. And we saw those olfactory bulbs from cranial nerve 1. B is just the axon of those olfactory neurons, okay? And C is the olfactory neuron itself. Right now, D would be the ones that are just kind of helping support this epithelial layer, right? So the supporting cells. E looks like those basal cells that we had in the tongue as well. So it is those basal cells there to replace the damaged cells. And then finally, F is the olfactory cilia, where we would where the chemical would actually bind. The chemical actually binds to those cilia there. And so this is all full of mucus right here, right? And the olfactory gland is releasing that mucus, right? And so the chemical hits that, gets dissolved, and then is able to bind to a receptor there on the end of those neurons. Okay. Questions about that? Yeah. Yeah, great question. So one of the symptoms of COVID in some people was anosmia, right? Which means you loss of smell. And what they found out was that the virus actually damaged these neurons completely, just kind of destroyed those neurons, and especially knocked out the cilia in those neurons to where in some cases they would come back, the cilia would grow back, but in other cases the neurons themselves were destroyed and they lost their smell forever. So did anybody have that symptom with COVID? Yeah, a few people. Yeah, totally. Anybody's like have it long term? Yeah, you can't really smell anything anymore. Good. Wow, that's crazy. Yeah, yeah, that's wild. Yeah, interesting. Yeah, Melissa. Hmm. Yeah, okay. Interesting. Yeah. Yeah, my guess would be that that is related to the loss of smell as well, because like a lot of our taste that we experience with foods is the smell. Is the smell of that food as well. So I wonder if it's just related to that in some way, like the ability to smell kind of changed, and so then that kind of changed the combo of chemicals that we were receiving to get the taste that we interpreted. But maybe something like that. But yeah, yeah, that's wild. Oh, I have heard about that. Yeah. 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 That is weird. Uh-huh. Flavored water. That's not really flavor. It's really smelly water. Yeah. Yeah. Good. Great. All right. Okay. So some more stuff about smell here. We can detect somewhere around 10,000 different smells. Oops. Which is way more than the tastes, right? Than the flavors. But the neurons stimulated by these different combinations are a much lower number of chemicals, probably somewhere in this range of the number of chemicals that actually stimulate those receptors. So what that means is it's a combo of the different chemicals that produce the different odors, right? It's not just a single chemical. This is much harder to research than taste is, because substances have to be in their gaseous state, which makes them a lot more dangerous and makes them more likely to cause damage to epithelial layers and things like that. So the pathway here is going to be that the molecule is always binding to some kind of receptor on the membrane in one of those cilia, okay? And then that's going to start that second messenger system. And then eventually that opens an ion channel and we depolarize. Okay, so in taste, it was this plus the direct pathway. In smell, it's only the second messenger system that is used. Okay, yeah, and so then the olfactory neuron is going to stimulate the olfactory nerve. And then we kind of split from there. There's a couple different tracks. One of the tracks goes directly to the olfactory cortex in our temporal lobe over here on the sides, right? But then the other track goes through our hypothalamus, through our limbic system where we deal with memory, and and you know this, that certain smells take you right back to a time in your life, right? You smell something, it's just like, oh, like I got emotional. I just thought when I just smelled that, or I feel like I'm sitting back in my grandma's living room or something, you know, like there's certain things like that because our smell is just directly connected to our emotions and our memories. And that's because this track to get it back to the temporal lobe goes through those places first. Okay. All right, so go ahead and chat about this one with the people on your team for a sec and send in your answer when you're ready.
Right, I don't have a reason, but I'm getting left.
Okay.
It's right. That's right.
For the whole like right brain, left brain thing, right?
Yes, well, okay, well, that's why I was wondering, I was like, is that real or is that?
That's true. Yeah.
Oh, it is.
Yeah. Yeah. There's truth to that. I mean, it's not like 100% true. There's truth to that. All right, go ahead and send it in. Just A or B here. All right, A or B. Go ahead. About 20 more of you still need to send it in. Okay. We're pretty split. We're pretty much split down the middle. About 45% of you are saying A, about 55% saying B. So yeah, so the pretty much the right brain has more, the right side has more emotional connections. The whole idea that like someone's right-brained, like a right-brained person is kind of like an artsy or more like emotional person is actually, there's some truth to that for sure. Your right brain has more emotional connections into the hippocampus and other areas, whereas the left side of the brain tends to be more with logic and reasoning and things like that. And so when they use their left nostril, they were more accurate. When they used their right nostril, they had bigger reactions to it. Because our cranial nerves don't cross in the spinal cord like our other nerves do, right? They just go directly to that side of the brain. With a motor neuron, it goes from the right side of the brain over to the left side of the body, right? But cranial nerves don't do that. They go directly to the side that they're on. So, okay, couple more things here. This was what we were talking about before. So there's some genetics involved in how we smell things. So cilantro, to some people, if you can't smell it, then it just tastes like soap. So there's a genetic mutation that makes it so you can't smell it at all. And if you can't smell it, then the flavor you get is actually just like a soapy flavor. Does anybody have that? They taste it? Yeah. Yeah. And so those people generally don't like cilantro at all, right? Is that the case with you guys? Yeah. Yeah. Alyssa, you too? You don't like cilantro or do you like it? Yeah. Really? Yeah, yeah, don't like it at all. Yeah, totally. And then we have this other chemical called ethyl mercaptan. And ethyl mercaptan is what we put, or what's put into propane. And so propane is actually like naturally has no smell to it at all. It's called natural gas, right? But it has no smell to it. But they actually put this chemical in it because it smells like garlic, like kind of almost like a rotten egg, garlicky smell. And it's just put into it to let people know when there's a gas leak, right? But it actually doesn't have that in it naturally. But unfortunately, some people can't smell it, so that it wasn't thought through very well when they decided to do that with propane. But yeah. Okay, and then anosmia, we've already mentioned anosmia. Anosmia is loss or reduction of smell sensation, can be congenital, meaning that you kind of are born without the ability to smell. But it can also be caused by trauma. So crushing of the cribriform plate can just slice through all those olfactory neurons and make it so you lose your sense of smell completely. So it can happen in car accidents for sure, when someone's face hits the steering wheel or the dashboard, that can just completely crush that, or yeah, with other facial trauma like that. But it can also other conditions that cause damage of neurons, like Alzheimer's, Parkinson's, schizophrenia, and then even some medications can lead to anosmia as well. And then we just got one clicker question left on the next slide. Whenever you're done with this, you can hop over there and start talking about that with your team. All right, this is another choose all that are true. So you can send in more than one answer, chat about that with the people on your team, and send those in and hit the send button. Aloha Friday, right now. Yeah. Are you in?
On a run.
You did. Gotcha. Are you in Tim Hall's class right now? Are you in Tim Hall's class right now? Yeah, that's what you're wearing the, yeah. All right, go ahead and send that in, hit the send button.
Yes.
All right, everybody hit send. There's about 10 more of you that need to send it in. We can walk through these here. So yeah, most of you put C, D, and E. So with smell, chemical can, yeah, what's going on? Sorry. Chemical can start the second messenger system, which eventually changes ion permeability, which just means ions can flow in, which then that leads to an action potential. So that's how it is in all cases with smell. With taste, some chemicals can directly open an ion channel or just go into an ion channel, making an action potential happen. And then also with taste, it can work via the second messenger system. So those are the three correct answers. All right, guys, have a fantastic weekend. We'll see you on Monday. Hey, all right, see you.